Okay, so I will further do some detailed explanation on the linear regression. By the way, this is not necessarily for the exam purpose, but just for your further information on the regression. So let me first plot the graph. Let's say there are these data points. And this is the regression line. And here you're seeing the regression line. Let me make it a bit thicker. So y equals a plus b times x. But here, let me use alpha plus beta times x. When we estimate, usually we put hats above for the estimation to differentiate with the actual value, right? So in this case, y hat would be the predicted value of y under this regression line. And let me say that we're interested in this point, and this is going to be xi, and let's put it as x1i so that we can differentiate with the other dots that are x1i, x2i, x3i, da da da. Okay, so x1i, and this part right here will be y1i. This is, by the way, the actual value of y. Okay. And then here, the y under the regression line will be the y hat, and more specifically, y1 hat given x1i, right? So this difference is called the u1i hat, okay? So u1i hat is the residual term that I have mentioned earlier. And u1i hat is the y1i minus the y1i hat under the regression line. Other way we can express y1i is y1i, it's just a repetition, but just putting numbers in different sides. y1i is going to be the sum of y1i hat plus a u1i hat, right? And the purpose of the regression is to minimize the sum of ui hat squared. So I said this is the sum of the squared residual, right? Let me rewrite this with the term that I have put right here. So instead of ui hat, let me put the yi minus the yi hat squared, right? This is going to be a minimum yi minus. Now let us plug in now this one right here, 2 stars, okay? So yi minus the alpha minus the beta xi star, okay? And we want to minimize with respect to 2 parameters, which is alpha hat and beta hat. Okay, and let me say this is z, okay? Z, by the way, is the square. I'm also including the square term right here. So this is going to be z. So we are minimizing this with respect to alpha hat, right? So differentiating with respect to beta hat. Okay. And by the way, these 2 equations are called the normal equation. With the 2 unknown parameter, alpha and beta hat. Right? So we are interested in estimating alpha hat and beta hat. So I'm not showing you, I'm not showing you all the detailed way of differentiating, but let me show you after the differentiation. After differentiation, what we get is beta. Beta is the slope that we are interested in, the relationship. Okay, so this is going to be the sum of xi minus the x bar. X bar is the average of x. yi minus y bar. So the average of y bar divided by the sum running from I equal 1 to n, xi minus the x bar squared. Okay. In other words, you don't have to know the formula, but this is simply covariance of x, y divided by the variance of x. So covariance of x and y shows the relationship between x and y. Variance of x is showing the variation of x. So this suggests how y changes with respect to, let me use the term WRT, the change in x. So that is what this basically means. Covariance x, y over variance of x. Oh, by the way, right now I'm only focusing on the simple linear regression. Okay, simple linear regression where we have only one x. And actually, in a real world, we have multiple linear regression where we have multiple x's. But for that, we need to know the linear algebra, which is outside the scope of this class. I mean, by the way, this is already outside the scope of the class. I just want to show you how regression works, as it's going to be heavily used wherever you go, including the industries and especially in academia. But there is a limitation of the regression, which is, let me bring back this sum of square residual formula. If we spread this is nothing more than u1 hat plus u2 hat, all over to un squared, right? So what does this basically mean? It's putting the equal weight to every u. But if you think about, say u is here, that's kind of off, right? So you want to actually put relatively greater weight to those points with smaller u's, right? But in the OLS regression, you're actually putting the equal weight. So this difference right here is also given an equal weight. Perhaps may lead to less accurate estimation, right? So again, in other words, error terms or the residuals that are far away from the line gets more importance compared to what? Than what they deserve. They actually deserve less weight, but they are given relatively greater weight, right? So that is a limitation of OLS. OLS is the ordinary least squared. And this is basically showing you to minimize the squared sum of residuals. That's why it's called OLS. Now let's move on to the goodness of fit. So goodness of fit was when whether the changes in the actual value y and the predicted value y hat is small enough, right? This should be small enough. For that, we use what's called the R-squared. Let me discuss what that is. Again, using the scattered graph. Here we have y, here we have x, and this is xi. Here we have actual y, the actual cost, let me say. And let's say after you put all the dots, in terms of y, you make an average of every y's, okay? So let's say the average of y is right here, okay? And this is called y bar. So this is nothing more than averaging across all i's in the data points, okay? Now, after the regression analysis, you get this estimated line, which is again y hat equal to alpha hat plus beta hat times xi. And here we are interested in the variation of y. Variation of y is expressed in the distance between yi, the actual term, and the y bar, the average. So how much does the y vary with respect to the average of y? So this is actually the yi minus the y bar is to express the variation of y. Okay, so this right here. And out of this, we want to understand how much this OLS, the regression model, can explain the variation. And actually, that variation is this part right here. Okay, this variation is what the model can explain. The model cannot explain the another part right here. Okay, so this part is the residual part. Model cannot explain. Why? Because essentially speaking, under this model, we are predicting y to be the y hat, right? So the variation that can be explained by the model is only the variation within the y hat and the y bar, okay? So let me formally write here. First, the total variation in y can be expressed as I minus y bar. And again, to express the variation, it's better off to do the squared, right? Because otherwise, things can be canceled out, right? So running over I equal to 1 to n, this is the total variation of y. And officially, it is called the total sum of squares. And we use the abbreviation TSS. And we can also officially explain the variation that can be explained by the model. So the sky blue part right here, right? So that's also running over I equal to 1 over n, and that's yi hat, right? Minus the y bar. This is the only part the model can explain. And we say it as the explained sum of squares, or the ESS. All right. And then lastly, we want to also express the model the variation that model cannot explain. So the red part right here. And that is y equal to 1 over n yi minus the yi hat, right? So this is the residual. Residual is something that cannot be explained by the model. Residual sum of squares. The variation that model cannot capture. So RSS. So by the way, the TSS is equal to the ESS plus the RSS. And R squared is nothing more than ESS, the explained sum of squares over the TSS, right? So for example, if this is 0.7, that means that 70% of total variation in yi can be explained, is explained by the model, right? So that is essentially the meaning of R squared, the important metric for the goodness of fit. And I said that in the post-evaluation part, we want to also evaluate whether the relationship is significant. Especially, I mentioned about the statistically significant part, right? Oh. Statistically significant. And for that, we do what's called the hypothesis testing. Hypothesis is, let's say, hypothesis is just like guessing whether the beta, the slope, has any relationship. Beta is, if the beta is equal to 0, then we're guessing that there is no relationship. If beta is not equal to 0, we are saying beta, there is a relationship between x and y, okay? So hypothesis is nothing more than a guess. It's a guess of anything that you want to predict, okay? So more in a statistical sense, it's a guess about the beta, unknown beta. If we assume beta is equal to 0, meaning there is no relationship between x and y, then we say that we are establishing what's called a null hypothesis. Null essentially means 0, right? We are saying that there is no relationship. And the goal here is, if we want to find that x and y has relationship, then desirably, we want to have beta that is not 0, right? So the way we form a hypothesis testing is trying to see whether we can reject null hypothesis, right? So this is also called H0. And sometimes you can say, beta, you can guess the beta is not equal to 0 in the first place. So this is called the alternative hypothesis. But usually in the statistics, you first guess that there is no relationship, and the goal here is to reject the null hypothesis. Okay? So to get rid of any confusion, I'm gonna just write down beta equal to 0, and we're trying to assume that, there is no relationship. And then our goal is to see if we can reject the null hypothesis, meaning beta is, we are rejecting that beta is equal to 0. So there is likely a relationship between x and y. We cannot certainly say that beta is non-zero. Rejecting null hypothesis cannot be confidently said as saying, okay, there is a true relationship. But the only thing that we can cautiously say is that we reject the null. Then how to reject the null? In order to do that, we need what's called a test statistic. And in our sense, this is the p-value. There are many test statistics, but p-value is used. The test statistic is the statistic that can help decide whether to reject or not reject the null. Oh, this is J. So, and p-value is used for the rejecting or not rejecting the null. Then how can we, p-value can be used, and also the t-stats can be used. Okay. So t-stats is the can be calculated as beta hat that we have got minus the hypothesized value under H null divided by what's called the standard errors of beta hat. I'm not going to go deeper, but this is the standard error of beta hat. Okay. The hypothesized value under null was nothing more than 0, right? We were guessing that beta is 0 under H null. So this can be summarized as beta hat over the standard error of beta hat. Okay. And we assume that this follows what's called the t distribution. Well, you may have heard of normal distribution, and normal distribution is a bell curve, right? T distribution looks very similar to normal distribution, but with a bit more fatter on the right and left side here. Okay, but it really looks similar to normal distribution. And there is actually a t distribution table, where you can infer some numbers, and you have to infer those numbers in our cases. So let's say this is the t distribution, 0 here, and we are assuming that under H null that beta is equal to 0, right? The reason why we're doing the t-stat is because beta itself cannot be measured across different data points. I mean, beta can be always very different because the magnitude of y and x's are all different, right? So we want to standardize to t-stat and see if our t-stat is significantly greater than 0 or less than 0, right? So I said the purpose of null hypothesis is to reject the null, meaning we want to reject that beta is equal to 0, right? And by the way, under H0, beta is assumed to be 0, meaning that the t-stat will also be 0, right? So if H0 is correct, then it will be around this point, right? But we want to show that it's not the case, right? It's either here or here where we can reject the null, right? And this is where we can say, oh, x and y possibly has relationship. Right? So for that, by the way, this part right here, where the null hypothesis can get rejected, is called the critical region. This part that I have set out as blue is called the critical region. So under the critical region, we can reject the null and say that the x and y has possible relation, right? Then how can we define this point? We need some kind of benchmark, right? For that, we need what's called the level of significance, alpha. We want to make sure that alpha is almost close to 0. Let's say it's 1%, 5%, or 10%. If you say it as 10%, then your critical region may be here. So you start off from maybe relaxing and expanding the critical region. So maybe this is 10%, and this is 5%, this is 1%. So if you say that, you're rejecting the null at the significance level of 1%, it's highly likely that there is a really strong significant relation between x and y. But if it's 10% region where you can only reject the null, then there is some weak significant relationship between x and y. So the more alpha is closer to 0, we can more safely say there is a statistical significance, right? Then once you have the level of significance, you may have to look up the T distribution table, where it shows you what is going to be this tabulated value of T. At the certain significance level. Okay. So for this one, you need to look up a T table. So let's say, for example, we have to set the alpha in any way possible. So let's say we set up the alpha to be 5%, right? Then that means that the region on the right-hand side would have 2.5%. Here we also have 2.5%. So once you set up, you go to the T distribution table, and look up what is the tabulated T for alpha being when the significance level is 0.5. So the T table, I cannot show you here, but you can actually look up, and you will see lots of numbers there. And there is what's called the degrees of freedom. And this is usually in a simple linear regression analysis case. It's the n-2, meaning this is the number of observation. Two is the parameter that we set, alpha and beta. So we already have alpha and beta, and other than that, other number of observations can have freedom. Like how many degrees of freedom in your observations you have. That's like sort of the degree of freedom. And you will see the degree of freedom here, 1 through all the way up to thousands. And here you will see the level, like the probability, cumulative probability. So cumulative probability. So here, let's say if it's 5%, we want to keep 2.5% on the right tail and 2.5% at the left tail. So you can look up at 0.25, perhaps right here. And given some kind of degrees of freedom and 0.25, you can look up the number. And that's going to be the number that you will plug in here and here. Because it's symmetric, you will have, if this is like 1.69, then this is also going to be minus 1.069, something like that, right? It's symmetric. Okay. So once you decide what the tabulated value is, then you can calculate the t-statistics that I have shown you, which is beta hat over the standard error of beta hat. And you want to make sure that this t-stat is greater than the tabulated value of t under the t table. Since the t-stat itself can be negative value, let me put the absolute value here. So in this case, when the t-stat is greater than the tabulated t under the t table, then we can reject the null. Right? And we can say that the x and y has a statistically significant relationship. Statistically significant relationship. So there are some technical things that I haven't really laid out everything in detail, like the standard errors of beta hat and like degrees of freedom. They I guess are more technical things that you can look up to. And if you are more interested in knowing more about it, including the multiple linear regression, I suggest you take a statistics class or the econometrics class, and hope that it would help you in the future. Okay, then I'll stop here and I will see you next class.